Okay, so we're going to talk here about the diffusion equation. So the diffusion equation is the same as the heat equation, and I'm sure you've studied this before. So C is the concentration. It's usually the heat equation is usually the first PDE you meet. All right. So, what is the diffusion equation? It's dTc is equal to some diffusivity, some constant, times the Laplacian of C. Now, the case we're considering is some kind of a long sort of tube here with only one dimension. So you can imagine here we sort of going out to infinity here in this direction. And we drop a little bit of dye into the tube and it diffuses out like that. Okay, so we only have one direction, which is x. So we've got C as a function of x in time. So this just becomes dx squared C. Okay, and this is exactly the same as the heat equation. This is the heat equation. Okay, the diffusion equation or the heat equation. So the only thing is that x goes from minus infinity to infinity. Normally when you first meet the heat equation you have boundary conditions and you separate variables and you get Fourier series. And since it's infinite, maybe it's no surprise that we end up with the Fourier transform. So now we take the Fourier transform and what do we get? We get the time derivative of c hat, because the Fourier transform is in the x with respect to x, and this becomes the derivative with respect to x is multiplied by ik, so it becomes minus k squared d c hat. Okay, no problems, and we can solve that immediately because it's not no longer a PDE, it's an ODE, right? And we get c hat is equal to c hat naught e to the minus k squared dt. Now the only problem is, what is c hat? Sorry, what is c naught hat? Well, that's just the Fourier transform of the initial condition. Okay, so we've got to start out with some initial distribution, so it's the Fourier transform of c of x comma t at t equals 0. All right, and we can solve this equation here. So we know that c is the inverse Fourier transform. Let me write it out explicitly. C of x comma t is the inverse Fourier transform of this expression here, and the inverse Fourier transform of two expressions is the convolution. So it's the convolution of c of so we'll call this just some notation here. We'll call c of x comma t at t equals 0, the initial condition. We'll call this c naught of x. Okay, so the inverse Fourier transform of this is the convolution. So it's c of x. This double star means convolution of the inverse Fourier transform of e to the minus k squared dt. Now, one of there is an exact expression for the inverse Fourier transform of e to the minus. Trying to get that. 2 looks a bit weird. There's an exact expression for the Fourier transform of e to the minus k squared d. In fact, one of the cool things about the Fourier transform is the Fourier transform of a Gaussian is a Gaussian. Okay, and just to recall here, changing colour, that f convolved with g is the integral from minus infinity to infinity of f of x minus s times g of s ds. Okay, and so combining all that we end up finally with c of x comma t is equal to 1 over the square root of 4 pi dt integral from minus infinity to infinity of c naught of s times, and you can swap the x minus s and the s, it doesn't matter where they go, it's got to have that symmetry, over 4 dt ds. Alright, so there's the exact solution to this equation, okay, to the diffusion equation written down as this convolution, and sometimes this is called the Green's function. This thing here appears as a constant, which I just pulled out the front, but this combined with this part here is the Fourier transform, the inverse Fourier transform of this Gaussian. You see it's a Gaussian, it was a Gaussian in K and it's a Gaussian in X here. Okay, and the inverse Fourier transform of this would be equal to, with an X, but I've used the convolution formula.